Qinghua Lei from Uppsala University in Sweden, talking about multiphysics coupling in geothermal reservoirs. So please give your attention to Dr. Lei.
Okay, so good morning, everybody, and I hope you can hear me. And it's really a great pleasure for me to be here to give this talk, and thanks very much for the invitation by the organizing committee. So today I'm going to talk about multiphysics coupling. And my research is more focused on fractured rocks, and I'm a rock mechanics guy. I'm also a numerical modeler, so I'm interested in modeling many different physical processes, including geomechanics, flow, solid transport, seismic waves, and with application to landslides, rock bursts, geothermal energy, the fluid injection, which I will show in some of my results today. And then I also work on tunneling and earthquake triggering and classification, etc. So today's talk will be more focused on geothermal energy. So what is geothermal energy? I think Peter has given a very good overview already. So here, if we imagine we have a cutter to cut the earth, then we can see it's pretty hot inside. And geothermal energy is basically we want to extract this heat from the subsurface and then convert it to electricity so that we can use it for our kind of living, and then this won't create any kind of CO2, etc. So it's a very kind of preferred renewable energy. So geothermal energy has been recognized as an important solution to help us to mitigate the global warming. So by using geothermal energy, we can possibly maintain the temperature on the earth, and all the animals, they can enjoy the good life, and we can still use the electricity for our life. So Peter already mentioned there are several types of geothermal resources. The shallow geothermal resources, which is kind of within the 400 meter depth, and it's often called heat pump, and usually for the residential use. And Peter has given very good overview about this. And my talk will be more going to the deeper subsurface, where we have the hydrothermal resources, and then the other important is the enhanced geothermal system, which is much deeper, larger than 3 kilometers. And the tricky thing with this enhanced geothermal system is that it's often in the hot dry rock. So the temperature is very high, but we don't have too much kind of fracture. We have fractured, but they are not so permeable. And it's very hard to circulate water. So we have to do some engineering to be able to use this kind of geothermal resources. So this is a typical setup of the EGS, where we have an injection well and a production well. So we inject the water into the target reservoir, which is 3 kilometer to 10 kilometer depth, normally 3 to 5 kilometer. And we somehow try to stimulate the fractures inside this reservoir so that they can form a kind of connected pathway to link to the production well. Then we can circulate water, we inject cold water, and then produce hot water from the subsurface. So this is the basic concept. And a lot of EGS projects,
what is the reason to go deeper if in the shallow groundwater you can already find enough temperature?
There is a kind of difference in the temperature here. So for the enhanced geothermal system, you can go to beyond 100 degrees so that you can have the vapor. generated, this can help you to generate electricity. For the shallow geothermal resources, it's normally for the residential use, it's okay, but not for electricity generation. Yeah. So the EGS has kind of been exploited across the world, although it meets a lot of challenges, especially, for example, the induced large earthquakes. For example, we can see some of the famous ones like Puhang, and many of them in Switzerland, I think Basel and Schöngarten, they got shut down because of the induced earthquakes. But it's still a promising kind of technology that we should further develop to use the deep subsurface geothermal energy. The steps for create an enhanced geothermal system and also use it includes mainly three major steps. First, we try to identify a preferred reservoir, and then we create a kind of injection well into it, and we inject the very high pressure fluid. This will help us to either create new fractures or stimulate the pre-existing fractures. Both will create the permeability or enhance the permeability. After that, it will be the third step is the production phase of the EGS, is that we inject the cold water and then produce the hot water. Okay? Then, because these reservoirs, they are in a very deep subsurface, 3 to 5 kilometers, it's very hard to know how they look like. We may have some kind of deep boreholes drilled into the subsurface, but with very limited information. So quite often we have to rely on some of the exposure on the ground surface to guess how the rock would be in the deep subsurface. So this is how it looks like the rock, the crystalline rock look like on the ground surface, where we can see a lot of faults which are characterizing the rock mass. And if we go into one of the fault zones, for example this one, we also see a lot of fractures. So basically, faults and fractures, they are everywhere in the rock mass. And this can true for the near surface or the very close to the ground surface condition, and also in the deep subsurface. It's just the fracture density may slightly or kind of decrease when we go into the deep subsurface, because for the surface we have also some effect like weathering. They can cause the higher fracture density. But this could be a good analog for us to at least know, okay, in the deep subsurface there would be a lot of fractures. And here, these fractures, they are not purely randomly oriented and placed over the space. They are organized, pretty much organized, because these fractures, they are initially created by the mechanical processes. For example, tectonic movement, which kind of stress the rock, the original rock, and cause the faulting and also the fracturing inside the rock. And here is some kind of analysis of the fracture length distribution, which shows the nice power law distribution, which indicates a strong kind of fractal behavior of the rock mass. And this is a very classical plot of the damage zone, of the fault zone, where we see in the middle is the fault core, around it the damage zone. So this is a big fault, and inside the big fault we see a lot of fractures. And these fractures, they are kind of subsidiary discontinuities belonging to the major fault zone. Okay. So these fractures, in other words, fractures are present across many different scales, from the tens of kilometers or hundreds of kilometers down to the centimeter, and they are also organized spatially. So one related question is, how can we represent and how can we model such a fractured rock mass? Can we model it as a continuum, or should we model it as a discontinuum? This is a very fundamental question and has a lot of debate on it in the modeling community. So people said that the discontinuum model, they are more kind of close to the reality. So if you use this, you can kind of represent the reality in a more accurate way. And continuum model, maybe it's less accurate, but it's more efficient. Kind of because you don't need to represent all the discrete structures in the system, which has less computational requirement. However, I would like to say more about this, is that it's not only the difference between the discontinuum and the continuum model is not only about the quantitative accuracy, it's also about the qualitative difference. More is different is because we have a large number of components in the fractured rocks. So because of the presence of this large number of components, the system can exhibit different, qualitatively different behavior and phenomena. And this is a concept proposed by Philip Anderson about 50 years ago in the context of condensed matter physics. And I think this can be applied to fractured rock masses because the fractured rock is also a complex system. And here he mentioned that for such a complex system, we are confronted with the twin difficulty of scale and complexity. And at each level of complexity, entirely new properties appear. So this concept lies at the heart of the mechanism which is called emergence. So basically, because of the interaction of the different components in the system, when we go to the upper scale, larger scale, or upper level, we can see different phenomena. So for fractured rock, we are quite often interested in the large-scale properties, like permeability, modulus, strength, heat exchange coefficient, etc. So quite often, we use some kind of effective medium theory to calculate the upscaled properties. But we have to be a little bit careful here, because effective medium theory couldn't predict the emergence of the diverse phenomena and property, because it's based on assumption that the system is in one regime. We have to consider the possibility of the emergence of different regimes. This is very critical, especially when we are analyzing a system which is close to or even going out of the equilibrium. So especially when the stress is quite critical, when the fracture system is critically connected, and this could be the scenario during the EGS. Right? So to be able to better understand the large-scale properties, we have to go to the small scales. Although we will increase the complexity, but this could help us to understand the origin of the different kind of macroscopic phenomena and properties in the system. Okay, so this is the pioneering work by Philip Davy. He once looked into the fracture network and characterized kind of the behavior of the fracture network based on the fracture length exponent, which follows for the fractures, they follow the power law distribution. So when this power law length exponent is small, the system is characterized by large fractures. And for this case, we can so basically use the relatively like the Snow equation, which is based on the kind of parallel and persistent fractures, more dominated by the large fractures. So we can use this type of model to do the analysis. On the other hand, when A is large, then it will be dominated by the small fractures. In this case, the percolation theory could be applied. And in between, probably we have to use the DFN model, discrete fracture network model, to capture both the small fracture and large fracture. So here you can see, because of the configuration of the fracture network, the system has different regime, and for each regime, the models has their own kind of constraint regime to be used. Right? So we can't make an assumption that the model can be applied to the other regime and then we use it to make the prediction. We have to be careful with the constraint of the application domain. And because of this kind of complexity of the fracture network, it can also exhibit the connected regime, disconnected regime. And this has fundamental control on many multiphysical processes in the fracture media. For example, here, when the system is poorly connected, the stress field, they are quite homogeneous in the fracture media. Okay? Because the fractures, they are very hard to sleep and interact with each other. And also for this case, the fractures are quite small. So the interaction is very small. And when the system is well connected and also critically stressed, we see a significant increase of the deformability of the rock mass. And on the stress field, we can also see a strongly heterogeneous stress field. Similarly, for flow, when the system is poorly connected, the permeability is quite low. Okay? The flow is much more controlled by the matrix. And when the system is well connected, we see these large fractures, they are under stress, they are also become highly sheared and producing kind of serve as the preferential pathway for the fluid flow. And we see a significant increase of the permeability in the system. Okay, so we can see the emergence of the diverse kind of regime in the system, and for each system, the different equation can be applied. Here is another case. It's the seismic wave propagation in fracture media, where we can see when the dimensionless frequency is low, we see the waves, they are in the kind of governed by the forward propagation. And when omega increases, we see the wave is diffusing. And then when omega is large, it will enter into the Anderson localization regime, which is basically the waves would be trapped in the system. So this is another example to illustrate the possible emergence of diverse phenomena in fracture media, which is because of the interaction, because of the presence of these fractures in the system. Yeah?
Can I ask you a question?
Yeah.
In all these studies, they are just dry fractures or they are saturated?
So in these cases, they are dry fractured, but for the flow, I show is that we model the fluid flow. But for this wave propagation, it's dry fracture. It's just I use some example to illustrate this kind of diversity of the emergence. Yeah. So in the context of the complexity, the fractured rock, often we think, compositionally, we think rock mass equals to the fractured plus intact rocks. But in the context of complexity, this may not be true. So I would say rock mass is not just a simple superimposition of fractures plus intact rocks. So in the past, we have gained a very good understanding of the behavior of the individual rock and fractured based on extensive laboratory experiment and also theoretical studies. We can describe the constitutive response of the rock deformation, fracture deformation, crack growth, thermal power elasticity, wave transmission, etc., etc. On the other hand, we quite often, when dealing with the application problem, we have to predict, estimate the large-scale properties. But we often found great difficulty to use the lab data to extrapolate, to make prediction. And quite often we attribute this difficulty to the scale effect. But I would say it's not just only about the length scale. This scale effect is also related to the physics, which is the mesoscopic interaction in the system. So this mesoscopic interaction, it brings together all the different fractures. It basically captures how the fractures and interact, they communicate with each other, they interact with each other, and how they co-evolve over time in the system. And these interactions includes several different multiphysical processes like stress transfer, fracture interaction, pressure diffusion, heat transfer, wave interference, etc., etc. And multiphysics coupling is somewhere here to help us to bridge the small-scale behavior of the fractures and rock to the large-scale properties of the system. So this is, I would position the multiphysics simulation, the role for the analysis of the rock mass behavior. Okay, so to do the analysis, we need to first understand the behavior of the component at the support scale, which I call it macroscopic level. So here, just want to clarify that this macroscopic, mesoscopic, and macroscopic is not defined based on the absolute length scale. It's more based on the population scale. So this macroscopic level is more about the individual component in the system. And macroscopic level is more about the entire population of the fractures. And inside this system, you can have large fracture, you can have small fracture. They can have very different length scale, from the kilometer to the centimeter.
When you have that equation that says rock mass does not equal fractures plus the background,
Yeah.
what else is it missing? I think I missed that.
So rock mass equals to fractures plus intact rocks. This is a kind of conceptual equation assumed in rock mechanics community for many decades. And because compositionally we think the rock mass behavior should be these two components plus together. But what I want to say is that here it's not only about the two things together, it's also because they can interact with each other. So this creates what is called more is different. So it can lead to the emergence of diverse behavior properties which we can't predict based on the individual components in the system. So this is also the concept of the emergence. Any other question? No? Okay. If not, then we move to the macroscopic level. Okay. So this is at the support scale of our analysis. It's the single fracture or single rock block. For the single rock block, it's relatively kind of straightforward, so I won't put much emphasis on this. So I will talk more about the single fractures. So here, it's a lot of research have been done about the behavior, especially mechanical behavior of single fractures in the rock mechanics community. And here is a kind of classical figures derived from the experiment about the normal deformation and shear deformation of fractures. So when we load the fracture sample, it will either normally close or it can also tangentially shear. And the kind of complexity of this behavior, the complex behavior of this fracture deformation arises from the intrinsic roughness of fractures. So this is why we see a strong nonlinear behavior of the fracture closure. So here, the y-axis is the normal stress, x-axis is the normal deformation or the normal closure of the fracture. So we see it's kind of curved up, which indicates that the more we compress the rock, the fracture, the more difficult we can close it. This is because when we close it more, the asperity, they will match with each other, get in touch with each other more, and they have more contact areas, and this will increase the fracture stiffness. And this plot is the shear deformation. So when we shear a fracture, because of this roughness, they can create some kind of aperture or dilation. This is the so-called shear dilation effect. Okay? So you can see these kind of gaps are created by the shear. And this is also a key mechanism of EGS stimulation, which is the shear stimulation, by opening fractures through the shear displacement. And I will talk about it in more detail later. Okay. And then, as we know, this is the experimental observation. To capture this kind of complex nonlinear behavior, several different models have been proposed to describe the constitutive behavior of the fractures. This is the models for the normal closure, including the Goodman's model, Button-Bandis model, exponential model, and the logarithmic model. So quite often for computer modeler is that how could we select a model? So we did kind of a compilation and comparison of the different models. What we found is that this logarithmic model, probably we can drop it because it didn't capture the increased stiffness behavior for some of the scenarios. And for these three, they are all supported by some experimental data. So I would say it would be a little bit hard to say which model is definitely better, but they all capture this kind of nonlinear behavior. But Button-Bandis model is more popular and used in the rock mechanics community. But exponential model, I would say, is also a good selection. Then regarding the shear deformation, there are also several different types of models. The simplest one is the modified linear elastic model. So in this case, we define a kind of virtual shear threshold, shear stress, kind of shear strength. And then when it reaches this, we further kind of calculate the exceeded shear stress, and this could allow us to calculate the shear dilation. This can be embedded into the linear elastic simulators like finite element method. But the tricky thing is that the actual shear stress, it can go much beyond the plastic shear stress. So although it has a very good convergence, but may not be a good model to capture the full physics. And the other is the elastoplastic model, which can capture this kind of plateau behavior of the shear stress. And then the Goodman model can capture the softening behavior, and Barton-Bantis model, which can capture more clearly the nonlinear behavior of the shear deformation. So from left to right, the complexity of the model becomes higher. And so the implementation also becomes more difficult, and also more difficult for the solver to calculate. So the selection would also has to be based on the convenience of your model, and also what kind of problem you want to solve. And the next thing is the fractal propagation. There are two criteria. One is the Griffiths energy criteria, and the other is the Moore column failure criteria. So this Griffiths energy criteria can be implemented into the discrete fracture models, and then the Moore column failure criteria can be included into the cohesive model or in the damage mechanics model. So having talked about the mechanical behavior of the fractures, now we come to the fluid flow, and this is the cubic law. I think everyone knows this. And so basically, based on the cubic law, we can derive the permeability of the single fracture, which is related to the aperture. And it just don't get confused with this Snow equation, and it also has the power 3, but the cubic law is based on the flow rate in relation to the aperture to power 3. Okay? So this provides a quite straightforward way for us to calculate the permeability based on the aperture. The aperture can be derived from the mechanical deformation that we have just talked about. And then we come to the last part, it's the heat transfer in single fractures. There are two kind of popular approaches. One is the local thermal equilibrium approach, which basically assumes the fluid phase and solid phase, they are locally equal, always. But this may not be directly applicable for EGS problems, because in EGS we often have the high gradient of the temperature. And so we may not always have this kind of instantaneous equilibrium. So in this case, we can use the Newton's law of cooling to consider the energy flux from the solid phase to the fluid phase through the fracture. Okay. So these are some fundamentals. Okay. So I guess many of you are are very familiar with them. And then apart from this, then we also need, the second step is that we need to model the mesoscopic interaction in the system. So by capturing the constitutive behavior, we know how each individual perform, and then we need to model how the individuals they interact with each other. This requires the multiphysics or THM coupling. So here, this T thermal hydromechanical, these different processes, they are interrelated with each other. Okay? And they can be described by these kind of fundamental governing equations, from the solid deformation to flow to heat transfer. And they can also be coupled with each other through, for example, here in the solid deformation model, we consider the thermal expansion, and in the fluid model, we consider this volumetric change. And so this allows us to link these different kind of governing equations together. So for the multiphysical coupling, there are two types of coupling. One is called direct coupling. This is through the governing equations. They can interrelate it with each other directly through the field variables like temperature, deformation, or strain, and the fluid pressure. The other important type is the indirect coupling. The indirect coupling is different from direct coupling in the sense that the coupling is through the change in the properties. Okay? So, for example, if you have the mechanical deformation occurring, for example, you open the fracture, then your aperture would increase. The aperture increase would cause the permeability change. So this is the indirect coupling. Direct coupling is that you have the water pressure increase in the fracture. This will also increase the kind of power elastic response inside the rock. So this would be the direct coupling. And both mechanisms are important for fracture rocks. And here you can see in the fracture rock in the EGS system, both direct coupling and indirect coupling, they are present and they occur in a quite diverse way. So for example, here, let me try to power elastic matrix deformation. This is the direct coupling. And we also have the fracture aperture change due to the thermal elasticity. This is indirect coupling. Yeah. So how can we kind of put these different processes together? It's quite complicated. Okay? The best way is the fully coupled model. Okay? So we solve all these equations together, but it's very challenging. Okay? To simplify this a little bit, people also developed this so-called iterative coupled model. It's often called two-way coupling. So in each step, you solve one field, you pass to the other field, solve it, and then it's feedback, and then you can have this kind of two-way coupling. But this could also be computationally expensive and may not be necessary for all the scenarios, especially if you only have mechanical is mainly controlling the flow when the fluid pressure is very low. In this case, you can use the explicit coupling scheme. So you solve the mechanical model, you calculate the aperture distribution, and then you use it to compute the flow. And you don't need to have your flow to feed back to the mechanical deformation. So this makes the coupling much easier, but this should be based on the scenario that the two-way coupling effect is not significant. But for fluid injection, for example, it will be significant. And we have to use either the iterative coupled model or fully coupled model. So we have come across the fundamentals of the modeling from the macroscopic description of the individuals to the mesoscopic modeling. And now let's look at the examples of application of the models to solve the problem. And here the main concept here is that we describe the behavior of the individuals at the support scale, and we solve the governing equation. We let the system to evolve. We let the individuals to interact in the system, and then they were this will allow us to capture the emergence of the different properties and phenomena in the system. The first example is related to the EGS stimulation. Okay. So the stimulation is that we try to inject high pressure fluid into the reservoir and try to stimulate the permeability to have an enhanced permeability. There are several mechanisms have been proposed about the EGS stimulation, including the pure opening mode. So basically there is no fracture, we just create a new fracture, like hydraulic fracture. The other one is the pure shear stimulation, is that we don't create new fractures. We just reactivate the existing fracture through the shear dilation, which what I just mentioned before also. And then the other one is that it's mainly dominated by the hydraulic fracturing, but with some of the small fractures also reactivated. And the last one is the mixed mechanism stimulation. So which one is dominant in geothermal systems? It's a kind of open question. Okay? To study this, people have done extensive experiments in the Grimsel laboratory to inject high pressure fluid into two shear zones or two fault zones. Okay. So this is the figure from Bernard's PhD, and he's also sitting there. Okay. So during this experiment, or before this stimulation experiment, he characterized the hydraulic properties of the system, of the two different fault zones. Okay. One is the S3, so one is the S3 fault, it's this one, and the other is S1 fault. The S3 fault is more connected, which is reflected by the higher fracture density and also the early arrival behavior of the pressure front. And the other shear zone is less connected and has a lower initial permeability. Then the interesting thing is that after the stimulation, we found the S3 shear zone, which is initially has a higher permeability, it has less permeability gain after the stimulation. Where for S1 shear zone, it's less connected at the beginning, but it becomes has more permeability gain after the stimulation. So it's a little bit contradictory. Regarding the seismicity, people also found in the S3 shear zone, which is the one which is more connected, it has higher seismicity level compared to the S1 shear zone. So what is the reason of this? Okay? So it's a kind of contrasting behavior of the two different fault zones. To understand this, I use my numerical model, which is the fully coupled hydromechanical model, to capture the coupled hydromechanical processes during the fluid injection into the fracture locks. So I used I modeled solid deformation. I used the damage mechanics model to simulate the fracture propagation. And I used kind of elastoplastic model, which I also mentioned before, to simulate the aperture evolution of the fractures. And further solve the flow equation with both the direct coupling through the volumetric change, power elasticity, and also indirect coupling through the aperture change or the porosity changes, etc., to have both effects considered in the model. And I further compute the seismicity evolution in the system by calculating using the classical earthquake equations to compute the magnitude of the earthquake. Here I have a kind of spatial temporal clustering algorithm to class, because some of the event may not be just created by one fracture slip. It can have several fracture slip or the damage. So I use this clustering to classify or identify the different events in the system. I validate the model for different aspects, from the fracture propagation to steady state fluid flow to transient flow and by comparing with the analytical solutions, and also for the hydraulic-driven crack growth, etc. So after I get a kind of confidence in the model, then I do a kind of benchmark test of fluid injection into a single fracture. So left shows the fluid pressure plot, where we can see when we inject water, it has some high pressure appearing at the taped region, and also some low pressure here. And the reason comes from the strong polyelastic effect. This is because we can see from here, when we inject water into the fracture, we will reduce the normal stress on the fracture, right? And this will also cause the slip of this fracture. When this fracture starts to slip, it will have a kind of compression zone formed, and this is the dilation zone formed. Because the background matrix rock had low permeability, then this increased the total stress would cause the overpressure. And this decreased total stress would cause the underpressure. So this is the reason why we see this kind of heterogeneous pressure distribution at the tape region. Yeah?
I wonder how much you recover of this stress if you release the pressure.
How much?
You recover this stress, and if you have here a mean stress on the left, on the right hand side.
Yeah.
If now you reduce the pressure, you fully recover the deformation that you, or the stress that you pose to the system.
Yeah, it's 90 megapascal, 46 megapascal. This is the stress. It's a 3 kilometer depth.
The question is, if you stop injecting
Yeah.
the water, the pressure drops, and how is the recovery of the stress?
Do you have any hysteresis in the process if you stop the injection of fluid?
Sorry, I still didn't get the question.
There should be, because there's damage.
The point is that you recover the elastic part of the stress, of the deformation. You don't recover the plastic part
The plastic part of the stress,
of the deformation.
of the deformation. But I use the damage mechanics model, so it's elasto-brittle model. So it can, when the stress exceeds the failure criteria, it will propagate the new cracks.
Is it like the real-time scale? So we need 1 hour to open a fracture to 50 megapascal? Is it?
Yeah, this is the real time. Yeah.
Okay. And
This is the 100-meter scale.
okay.
Yeah.
I thought it's much faster. It's such high pressure. It's like in a second.
Yeah. Yeah. Hey, so I further use this model to develop a kind of conceptual scenarios where I have a poorly connected system and a well-connected system. So one is below the percolation threshold, the other is beyond it. And I also put a lot of kind of monitoring points to try to understand what is happening in the system, hydromechanical responses. So I consider a depth which is 3.6 kilometer. And I inject the water for 1 hour. And the boundary of the system is the constant pressure. And I use the constant fluid injection rate. And here is the simulation results for the two different connectivity conditions. So for the poorly connected system, we can see a lot of damage happening in the system. What is happening is that when we inject water into the fractures or fracture rocks, the pressure quickly builds up in the local clusters. And then this will cause some of the fracture to shear and then they will propagate new damage or new cracks. They try to link with some other clusters in the system. Then finally, they form a kind of percolating pathway to connect to the boundary. And for this one, it's well-connected system. We didn't see too much new damage generated. This is because the system is already well-connected. So the pressure can already dissipate through the connected pathway through the system. So from this we can understand, right? The poorly connected system, it can have higher connectivity gain. So that's why it has a higher permeability gain. For the well-connected system, it will have lower permeability gain because it will generate less damage in the system, or less new cracks. Here, in this kind of, I monitor the pressure response at the injection and monitoring points. So this is for the poorly connected system. We can see these solid lines, they are placed on the fractures. Right? So we see the pressure quickly builds up at the injection point and then start to decline. It's because it will kind of reactivate some of the fractures to shear, and then the pressure start to spread. And then we see this kind of sharp increase. This is related to the connection of the pathway to some previously disconnected fractures, and this will cause them to quickly build up the pressure at a later time. The very interesting thing is this kind of pressure drop, which happens in some of the matrix. This is a clear indication of the strong poielastic effect. So these points, they are placed at the location where the new cracks, the created new cracks, will pass through. Before the new cracks arrives, the local region will be subject to tension. Tension will cause the under pressure. Because these new cracks, they are caused by the tension failure. So before they arrive, the tension stress build up and reduce the kind of pressure. And as long as the new cracks arrives, the pressure quickly builds up. So this indicates the importance of considering the hydromechanical coupling in order to understand the responses of the fracture rock. Here I also further analyzed the shear displacement behavior of the fracture rock. And you can see for this fracture set, they are preferentially oriented originally to have large shear displacement. But after the stimulation, the more reactivated fracture, they are the fractures which are less activated at the beginning at the in situ stress. And the reason is because if this initially more sheared or open fracture, if they want to form a connected pathway, they have to go through, the fluid has to go through this less open fracture. So they have to open up those closed fracture. So that's the reason why we see more shear displacement and also more aperture increase in this initially closed fracture rather than the initially open fracture. This is also a little bit contradictory to what we would kind of interpret or predict without using the modeling. So clearly, this poorly connected system, we have more damage generated, and this connected system, it has much less damage generated. And I want to move to here. Yeah. But when we plot the seismicity, we see, although this poorly connected fracture system, they have more damage, more new cracks, but the seismicity is low. For this well-connected system, it has less new cracks generated, but has higher seismicity level. The reason is because the seismicity is more dominated by the shear displacement and shear reactivation of the pre-existing fractures. Where the new cracks, they create much smaller magnitude of the seismicity. So this would also explain what we observe in the Grimsel field, where the poorly connected system, they have less seismicity. And here, this is a figure to further illustrate the connectivity changes, where we see after the stimulation, the poorly connected system has much higher connectivity gain. Okay. So, using the model, we have got a kind of good way to interpret the observation in the field. So this is also the strength of the model. We can also further analyze the underlying mechanisms of some of the observation or the simulation result. So one open question is why in this, for example, in this poorly connected system, why the damage, new damage, only initiate in some of the tips of the fracture? Because this initiation or propagation of this new damage, they are the region where we have the permeability enhancement and connectivity gain. And the reason is the power elastic effect, which drives the connectivity evolution. This can be clearly illustrated using this height expression of the fluid pressure evolution. So what is happening is that when we inject water into the system, the fluid pressure inside the locally connected cluster, it will quickly build up, which forms these kind of mountains. But where the new damage would go, it depends on the gradient of the pressure. And the gradient pressure would be dependent on the valleys, so which is the under pressure region. And this under pressure region is controlled by the shear displacement of some of the pre-existing fractures. So for some of the tip region, they can have the higher decrease of the pressure. This will cause a shallower, kind of much deeper valley in the pressure distribution, and this would drive the pressure gradient, and then the fluid go there to drive the new crack propagation. Okay. So we further use this model to also study the fluid injection into the fault zone, which is the more hierarchically organized fracture system, and where we can see also diverse behavior of the kind of pressure response and the seismicity pattern in the system because of this kind of hierarchical organization of the fault zone. And if we are very close to the fault core, the pressure, because of the high density of the fractures, the pressure can dissipate very quickly. And if we stay a little bit away from the high density fracture zone, we can even kind of create more new damage and a higher increase of the connectivity. And here this figure shows the kind of diverse patterns of the seismicity. So they are also strongly dependent on the injection point and also the organization structure of the fractures inside the fault zone. So the key message I would like to say here is that we have to consider this kind of organization and the interaction of these individual fractures, how they interact and how they perform and evolve in the system under the coupled hydromechanical processes for us to understand some of the phenomena, complex phenomena we observe in the field. Now we move to another application which is related to the geothermal production. Here I use a kind of explicitly coupled model. And so similarly, we model the geomechanical behavior considering the aperture and the shear deformation behavior. And we model the flow and heat transfer in the system. For the heat transfer, we consider the heat conduction inside the matrix. And we also consider the heat convection, which is more dominating in the fractures. We build also a conceptual model. This is a relatively small scale. It's the 10-meter block of the rock. And the key question we want to study here is that what is the kind of upscaled heat exchange efficiency? So how it can be affected by the stress, the geometry, and the hydraulic condition, etc. So we generate a series of fracture networks of different length exponent, and which leads to, and also different density leads to the different percolation or connectivity condition. Okay, so the left one, towards the left side, the system is more connected. Towards the right, it's more dominated by the small cracks. Here is the results of the aperture distribution, where we can see when we increase the stress ratio, so basically increase the differential stress from the 1 to 2 to 3, we see some large apertures are generated along the kind of long fractures. This is because of the shear dilation effect. These fractures, they are more prone to experience the shear displacement and therefore the shear dilation. And for these small fractures, they are more constrained by the matrix to shear and deform. So they are more subject to smaller apertures. So consequently, for the flow, we can see that so these large fractures, they form the preferential pathways for the fluid flow. Okay. Then if we look at the temperature distribution in the system, we also see contrasting behavior. If the hydraulic gradient is high, we see these kind of large fractures which are highly sheared, because they are the preferential pathway for flow. So we see this kind of temperature decrease significantly near these fractures. We see a clear coning effect, especially in some of the cases close to the percolation threshold, which is around 6. And for this disconnected system, it's more dominated by the heat conduction through the matrix, because the fractures, they can't play too much role in the flow and therefore in the heat convection. However, if the hydraulic gradient is low, we see all the systems, irrespective of these large fractures, they all have quite smooth thermal front. Okay? So this is because the flow rate is very low. And so in this case, the matrix, it becomes more dominant in the process. And for this high hydraulic gradient case, we also see a clear stress effect, which are more significant for this case, which are well connected. But for the other disconnected system, the stress seems to play very little role. Okay? So we further analyzed the outlet pressure, temperature. For the high hydraulic gradient cases, we see a clear spread of the behavior, and which is because of these large channels formed by in some of these kind of smaller A cases. Where for the other cases, they are more dominated by the matrix conduction. So that's why you have this kind of diverse behavior of the outlet temperature evolution. But for this low hydraulic gradient, it's more collapsed together. So we see quite different regime. And the overall recovery, it follows similar behavior that we have shown for the outlet temperature. And what I want to show is this heat exchange efficiency, which can be analyzed by plotting the average outlet temperature versus the overall heat recovery. And if this curve is bending upward, it will indicate a good heat extraction efficiency. If it's bending downward, it will be a bad efficiency. So what we can see is that for the high hydraulic gradient, when the stress ratio increases, the efficiency decreases. For the low hydraulic gradient case, when the stress ratio increases, the efficiency somewhat increases as well. So this also a kind of diverse behavior of the system. And we have to, so this THM model offers the way for us to capture the emergence of this qualitatively different behavior. We further also developed the fully coupled thermohydromechanical model, and which is at much larger scale. And we showed that the stress can have very important effect on the heat extraction. And conventionally, the stress, the geomechanical effect or the stress effect is quite often be neglected in the reservoir simulation. So we made a comparison with the roller boundary. So basically, we don't consider the stress effect. And what we found is that the aperture distribution and the evolution will be very different from what we see for the case with the stress effect. Okay? So it can significantly overestimate the aperture enlargement. This is because it doesn't consider really the compression of the caused by the stress. It's when the temperature decreases, the fracture would experience the kind of the rock experience the shrinkage, and then it opened the fracture. But there are the compression present, the shear present. This will take place. This would lead to kind of, if we ignore this effect, we will overestimate the aperture distribution. We will overestimate the flow rate condition, and we will also underestimate the heat extraction capability or capacity of the reservoir. And here in this simulation, we also could capture the important thermal expansion effect. So basically, when our thermal cooling effect. So when the thermal front propagates in the rock mass, it will cause some of the fractures. They will have the less or reduce the normal stress. This will cause the opening of the fracture, and also on the other way, it can also reduce the shear strength of the rock, because you reduce the normal stress, you reduce the shear strength. This would promote the shear dilation. So on the other way, it can also further increase the aperture. Okay? So this has been captured by our thermohydromechanical model. Okay, so take home message is that we should conceptualize a fracture rock as a complex system consisting of a large number of components, fractures, rocks. And it is important to consider, to understand and model the collective behavior of these fractures and rocks under the coupled multiphysical processes in order to capture the emergence of the qualitatively different phenomena and properties in the geothermal reservoirs. And multiphysics simulation offers a very good tool for us to link from the single scale, single fracture scale constitutive behavior to the large scale diverse phenomena in the geothermal system. Some outlook. So in the future, we would like to also explore 3D kind of thermal hydromechanical modeling of the geothermal reservoirs. So recently we have developed 3D models, but not in the context of geothermal system, but we applied it for the tunnel construction and also the borehole drilling, etc. And we hope in the future to explore the model for the 3D geothermal, either the stimulation or the production phase modeling. And the other important thing to consider is also the dynamic effect. So when we model the seismicity, the friction would not be quasi-static. In the lecture I mentioned, most of the constitutive models, they are the quasi-static model, which have been developed over the past decades in the rock mechanics community. But this kind of overlooks the dynamic effect, which we have to come to the geophysics community, which people have developed rate state friction, slip weakening models, etc. And we should consider this especially if we want to solve the problem like induced earthquakes. And I think Ruben, he will talk more on that next week. And another thing I didn't mention too much is the chemical part. And we have developed a quite robust thermal hydromechanical chemical model, more focused on hydromechanical chemical coupling with application to the karst evolution. And in the future, we may also explore it for the geothermal system. So having said this, that's the end of my talk, and I'm happy to answer any further questions. Thank you. Yeah.
One kind of philosophical modeling question. Would it be better to have the coupling at the single fracture scale, like to have the hydromechanical coupling, not in the continuum, kind of the mesoscale, where you actually have only the continuum questions?
Yeah, so it's actually, this is also a matter of the problem that you are interested in. So if we want to solve the engineering application problem, it will be very difficult to also model the detailed processes inside the single fracture. But it's important to understand the detailed processes. For this, we can also conceptualize a single fracture as a complex system which is formed by a lot of asperities. So we model the behavior of the asperities and then capture this kind of collective behavior in the single fracture. This can help us to inform the fracture system modeling. So I would say we should develop a kind of hierarchical modeling strategy. So this scale, it should not be based on the absolute scale, it should be more based on the system scale.
So like a constitutive relationship?
Yeah, so it informs the constitutive relationship, and then this can be plugged into the fracture system modeling.
Another question, you mentioned asperities. So how important is pressure solution? You actually have like this solution and real precipitation, and you are squashing these asperities without any kind of reactive.
Yeah, it's a very important topic actually. The pressure solution and the coupling with the stress, etc. So this I didn't cover in my talk, but it's a very active field, I know, and it's also important to consider how the aperture it will evolve under the interplay of pressure solution and the dissolution. How this would they will impact the aperture evolution, and it will be useful to kind of develop a detailed model and then inform the constitutive behavior that we can use in the larger scale.
So people think this is important for geothermal, so the pressure solution should not be discarded, and the kind of chemical gradient should be included in this.
For geothermal system, yeah, I'm not an expert in pressure solution. It's hard for me to comment on this, but it can be, yeah. Sorry.
That's okay. Thanks.
Yeah.
I have a question about these connectivity changes that you showed. These were computed at the end of the stimulation injection,
Yeah.
right?
Yeah.
And I wonder about the persistence of these changes once you stopped injecting. You said that a lot of the connectivity gain comes from shear displacement, but there's also, I guess, a portion that is due to the residual normal opening gain of the fractures. And when you stop injecting, I guess the system will relax and so the structure will close. So then over time, we would like to avoid injecting a lot, I guess, of water in the systems. We'd like to just do it once and then create a reservoir and then just circulate at low pressure. Have you looked at the sort of decaying time of this connectivity change, or are these permanent?
So here you mean it's kind of, we have you inject, then you stop, like a cyclic injection, right?
No, you inject, you stop, and then you looked at the changes in connectivity.
Yeah, yeah, this is what I
But then,
did.
if you don't inject anymore, the system over time will go back to its
the
usual
recovery.
state, right? The recovery of the connectivity
Yeah, yeah.
state prior to stimulation.
Yeah.
And people think shear displacement gives you like a permanent gain because you create this offset. But some of that connectivity also is due to a residual opening, I guess, of each fractures. And this should relax quite fast. So the question is, could you run your simulations longer and then recompute and see this relaxation and how much that contributes to the overall, long-term connectivity gain?
Yeah. So in this model, what I'm using is, I can go back to here. It's quite far way back. So if we want to model this kind of unloading behavior, we probably need to consider this unloading constitutive behavior of for example, the normal closure of the fractures. And for this, I still haven't implemented into my model yet. But I would say if the permeability is more dominated by the shear dilation or shear displacement, then this recover may play the minor role. So it really depends on which person. It's more controlled by the normal closure or the opening of the fracture under the fluid pressure, or is it more controlled by the shear slip due to the fluid injection? If the latter is more dominant, then this effect may not be so important.
And you said for the well-connected system that gives you a lot of seismicity, which is what we saw in the field, you got a lot more shear displacement than for the poorly connected.
Yeah.
But the initially poorly connected system got a lot more connectivity. So could it be that it's actually just really short because it didn't shear so much, it's actually more normal opening and then it closes, and so maybe it doesn't persist.
Yeah, so here this connectivity analysis, what I did is more geometric. So it's not based on the flow calculation. So it's actually, in the future, I would like to also do a kind of post-stimulation injection or injectivity analysis. Yeah. Yeah.
Well, thanks.
Yeah.
So my question is about the green cell experiment and the interpretation that you did of these observations that the less connected fault zone was the one that was that undergone the largest permeability mass. So your explanation was that this is because in the less connected system you have larger pressure increase and therefore you have more failure and therefore you create more new fractures, which I totally buy. But my question is, what about the effect of orientations? So the two fault zones, do they have the same orientation of the pre-existing fractures or do they have different orientations? Because that could also, because in your models you have always, for the poorly connected and the well-connected system, you always have the same orientations of two sets of fractures with the same orientations. And I was wondering, because of course this has a large effect. If you change orientation, then you don't fail in the same way, and some fractures are more prone to shear than others. So what about the orientation in Grimsel, in these two folds? Is it the same? Or?
Yeah, this I need to refer to Bernard.
And I think, yeah, that's also something we didn't really tackle so much, is the effect of the orientation, because they have really distinct orientations, and so they're oriented to the stress differently.
And so there maybe one orientation is more prone to fail, to shear fail than the other.
Could be, yeah.
It's a very important aspect. Actually, it makes very different in the reactivation behavior by the orientation. Yeah.
Can you show slide 68 if possible?
Sorry?
Can you show slide 68? I think they will
68.
clarify my question.
Okay. 68. Let me go to 68.
There's a factor missing there.
This one?
Yep.
Okay.
So if you stimulate your reservoir too much, you will have early breakthrough, right? Which is not good for the efficiency, I guess.
Yeah.
Right? So is there understanding of some optimum regime where we want to target for?
So the lowest efficiency is those which are very close to the percolation threshold. So because we can see there are some dominant single fracture. So this has a very strong coning effect. So this would be something we should try to avoid. But it's also a tricky thing because our crust is often quite close to the percolation threshold. This is something people often found based on the outcrop mapping. So yeah, this is the region that we should try to avoid to get. Yeah.
So can you discuss possible ways to engineer that? Like what if you created such a early breakthrough? Is there a way to redistribute such that you have more uniform flow? Like what are the mechanisms to engineer that?
So the possibility is that maybe you can stimulate it to have a bit more kind of pathways, and then this could help us to have kind of smoother thermal front and a larger sweeping area. So to do this, I think we also need to understand the initial connectivity condition, and to optimize the injection point. But how to optimize, I don't have a clear clue on how we can design the strategy of the injection. But it could be a very interesting topic to look into using the model. We can study different regime and the system and place the injection point at different locations and see whether we can have different behavior of the post-injection.
Maybe just one more question.
Yeah.
A kind of philosophical question.
Yeah.
You've shown a lot of particular results, and you've made the point that complexity is really important.
Yeah.
And many of your results are shown in dimensional terms: temperature, distance, time. And as more of an analytical guy, I'm much more interested in the phase space where we can actually go beyond the particulars. So can you talk a little bit about how to think of these, what are the steps to synthesize this into a more broadly interpretable set of results?
So yeah, that's a very good point. So regarding you mentioned phase space, right?
Yeah. So
And
dimensionless variables, where you say, what's the percolation threshold versus the aspect ratio of the fractures, or the orientation versus something where you're plotting competing variables that synthesize multiple effects.
So two important parameters based on some of the results is one is the percolation parameter, which controls the connectivity of the system, and the other is the stress ratio, which controls the individual stress or the criticality of the individual fractures. But I would say this is a relatively simple scenario, but we can also go more complicated, like phase diagram, which is, I would imagine it should have two control parameters. One should be related to heterogeneity, so basically how these fractures are placed in the space. The other is related to the nonlinearity, so the constitutive behavior of the individual fractures, the stress drop, the friction, the damage behavior, etc. There could be a kind of control parameter about that. And then these two may be able to help us to understand the system performance. But there might be a third dimension, it's the time, so the evolution of the system. But I would imagine it can be a challenge to create such a phase diagram, because phase diagram is represents the sum of the knowledge. So if we can build a phase diagram, that would be great. And then we know almost everything in the system. But this could be a target for the future to explore. Yeah.
Let's thank our speaker one more time.
Okay, thank you.